Okay, so now we're going to be taking a look at relating arithmetic sequences to functions. And we've been given a chart here. And so here in this chart is telling us the length of Martin's long jumps. And we see here that on his first jump, he jumped 8 feet. On his second jump, he went 9.5 feet. Third jump, he went 11 feet. Fourth jump, he went 12.5 feet. Martin is quite a leaper. And we're being asked to write a function to represent this arithmetic sequence. So I can really kind of consider that on this row of the jumps, so I can think about that as when I'm relating this to arithmetic sequences as AN. And that would make this A1, A2, A3, and A4. Now, if we recall, if we're trying to find a certain term in a sequence, we can use this, AN equals A1 plus N minus 1 times the common difference. So we know what A1 is. A1 is 8. So A1 is equal to 8 feet, A2 is equal to 9.5 feet, A3 is equal to 11 feet, A4 is equal to 12.5 feet. So A1 is 8. And let's see if we can determine what our common difference is. Well, the difference between 8.5 and 8 and 9.5 is 1.5 feet. And if I compare 9.5 to 11, I can see I still have a common difference of 1.5, 1.5. And the difference between A3 and A4, 11 to 12.5 is also 1.5. So I'm pretty well satisfied that my common difference is 1.5. So then I got AN is equal to, well, A1 is 8 plus N minus 1 times my common difference of 1.5. So let's distribute then this 1.5 to the N. So I got equals 8 plus 1.5N minus 1.5. And then let's combine the like terms of the 8 and the negative 1.5. And so I end up with AN equals 1.5N plus 6.5. 1.5 subtracted from 8 is positive 6.5. And then if I'm going to rewrite this as a function, I could then say that f of n is equal to 1.5n plus 6.5. Now, we're going to jump over to our calculator and graph this as a function. Now, in this particular problem, this gives us a bit of an improbability in terms of using this function as a predictive measure or predictive instrument, but we'll talk about that once we graph it. So let's get over here to the graphing calculator. Okay, well, I'm up here at my graphing calculator, and I'm going to make a few window adjustments here before we graph this thing. So we're talking about number of jumps. Well, I can't have negative number of jumps, so I'm going to set my x minimum to 0. And x is going to be equal to the actual number of jumps, 1, 2, 3, 4, 5. Well, I'm going to leave that at 10. I guess he could jump 10 times, surely enough. And on my y minimum, this is the number of feet he jumps. And tell you what, I'm going to go back to my x minimum because I'm not going to have 0 jumps. I'm going to say at least got 1. Let's set it like that. And let's see, go back here to my y minimum. Well, I'm not going to be jumping negative. We're talking about distance and not displacement. These are scientific terms. Distance cannot be negative. I can't have a negative distance. I can only have a positive distance. Now, if we were talking about displacement, just as a point of fact, that I could represent that as negative because displacement considers not only direction, but it also, not only distance, but it also considers direction. And sometimes when we're measuring displacement, we may have a negative to show that we're going in the opposite direction. But in this case, we're doing distance. So I'm going to set the y minimum. I'm going to go ahead and leave it at 0. Now, y maximum. Well, I know on that fourth jump he went 12.5 feet. So I'm gonna set the y maximum maybe at I'm gonna pick something arbitrary, but I want to be further than 12.5. I'm gonna say 24, twice as far. All right, that should do that. And I'm gonna go in here to y equal to graph this as a function. Remember, we did f of n is equal to 1.5n plus 6.5, and I'm gonna substitute x for n in here. And so let's see, I've got y equals 1.5x plus 6.5. Now let's go in here and take a look and see what our graph looks like. Okay, so remember we said x is equal to 1, and that was 8 feet. 1, 2, 3, 4, 5, 6, 7, 8. There's 8. Y is equal to, when x is equal to 1, y is equal to 8. And probably an easier way to look at this is going to be if I go into my table. Let's go table. And so jump 1 is 8.5 feet. We got jump 4, and x is 4 is 12.5 feet. And if we get out here to 10 jumps, we're saying that Martin is going to jump 21.5 feet. And maybe that's true, I guess. If it's a running long jump, I think maybe you could probably jump 21.5 feet. But there is a physiological limit as to how far anybody can jump. And this is kind of an interesting problem they've given us here to write this as a function, because I can intuitively know that at some point in time, I'm not going to be able to jump that far. Of course, I couldn't jump 21.5 feet, but there are people I think who probably could if they've got a running start, if they're doing a running long jump. Okay, well, we've written it as a function and we have graphed it. We've got some more problems coming up that I think are a little bit more reasonable than the one that we were given here, but hey, we've done it.